Haven't finished marking yet. Haven't finished marking yet. Think you do good or not? Do you think you do well? Gia đình chồng mình ẩm mà rất ẩm mà phù cái cái ẩm tính Okay, we should start now. So we got complaint that we end very late for this class because you guys come late and start late, right? So maybe we start on time and then later 9:50, before 9:50, if I haven't finished, please remind me, okay? So that we leave. Okay, yeah. Let's start first, then later we'll discuss a little bit about assignment, feedback, when all of you come. And midterm I haven't finished marking yet, so I'll probably have to wait until next week. Okay, let's start. Okay, so far we have gone through how many weeks? 7 weeks, about 7 weeks of content. And then we actually know quite a lot of things about groups already. Okay, so I mean, know a lot of things, meaning about some classification of group. For example, what kind of thing we know? Okay, we know that first very simple result is every cyclic group is abelian. Okay, so why is this a simple fact? This is just a fact on commuting the power. Okay, this is a fact of commuting the power. So you should imagine why this number commute. Right? This is in the end just r plus x on the power. So you can make it x plus r. Okay. And then second fact, we didn't prove, is a big result. So okay, a simple result is there's only two groups of order. Okay, so what are these two groups? So these are Z4 and Z2 cross Z2. Okay, or in other words, we can write it as cyclic group C4 and C2 cross C2. Okay, and then we can generalize this result here. Okay, how to generalize this result? So we say that every finitely generated, okay, and then abelian group is isomorphic to a product group. Okay, to a product group. So what is this? What are these product group? So these product group are cyclic group of all power of order of a prime Okay, and then crossway multiple of Z. Okay, we didn't prove this, but this is a classification of finitely generated Abelian group. Okay, so note that although I said finitely generated, right, but the element here could be infinite. Okay, just that we can use finite generator to build all the elements. For example, Z is finitely generated. Z is generated by 1. Okay, but in Z, there's infinitely many integers. Right? 1 to 100 billion. Okay, and then negative billion. Right? But we can use one element, 1 to generate. Right? It's the piano axiom. And then here say that if it is finitely generated and a billion, okay, and a billion, then this is isomorphic to power of 1. Okay, so this power should be this prime should be different. So you can see that you can find generator here. So some of them are finite order, some of them are infinite order. Okay, that is infinite. You can imagine the generator here is infinitely infinite order. Yeah, but one here at finite order. Okay. Okay, so you can see that we try to build groups using Z and cyclic group. Okay, cyclic group. Okay, so this is about a billion group. Okay, so far how many operation you see on groups? If I give you 2 groups, you can, or subgroups, you can take the union. Okay, you can take intersection. You can take product. Okay, so now we're gonna introduce division into group. Okay, how you divide groups. Okay. We will introduce a new things called the quotient groups. By the way, if you see my lecture note last week, right, I put some content that I never present in the class. I wrote there non-examinable material. Yeah. There's about 3 pages here. 1, 2, 3. If necessary, we'll come back. If not, we will just leave it. Okay. I will just leave it. You can read about it. For this class, but actually this knowledge is kind of important if you want to keep doing pure maths. You can read about it, but if I need it, I will introduce it again. Okay. Okay, so let's go into quotient group first. Okay, so what's the quotient group? So the quotient group here is actually the thing you already know. This is the set of coset. Okay, but this is a special coset. This is the coset of a normal subgroup. Okay, so we are slowly marching toward the statement that Ying made last time. Every normal subgroup is a kernel of some homomorphism. Okay, this is the statement we want to make, want to prove, probably today. 10 minutes later. Okay, every normal subgroup is a kernel of some homomorphism. Okay, last time we proved that every kernel is a normal subgroup. Okay, now we want to show that every normal subgroup is a kernel of some homomorphism. Okay, so the set of coset, okay, not random coset, coset of a normal subgroup only. Okay, whenever you have a subgroup, you can start and try and cut your groups or partition your groups. Okay, So this time we don't use random subgroup, we use normal subgroup only. Okay, remember there are good property that normal subgroup holds. What are the good property? Why normal subgroup? What are the property that this subgroup gives?
The number of the quotient equal to 9%.
This one is the general quotient. Yeah, normal. The TSAE statement.
TSAE. H is equal to HX.
SH equal to HS. Okay, so what does this mean? This means every left quotient is a right quotient. Okay, and then you can commute the SH with HX. Okay. So the set of quotient of a normal subgroup N, okay, of a group G is denoted by G mod N. Okay, so you always have to have a picture when I talk about quotient. Okay, you want to cut your group into partition. Okay, partition by N. Okay, here N is normal, and then A, N, Cn, and so on. Okay, this is the picture you should have in mind when I talk about quotient. And then so we will set some notation here. We will set G bar equals to G mod N. And then we will set the coset as A bar. Where's the first time you see something has a bar at the top? Equivalent class. Okay, we're going to see that this is actually those equivalent class. Okay, G bar, A bar. So the typical example we will have in this course is, in this subtopic is Zn. Okay, or Z mod and Z. I didn't realize that in your description they didn't introduce this notation to you, Z mod and Z. I thought you guys see it before. Because in class I only write Zn, right? Yeah, forgot you didn't know this. Okay, so this Z mod and Z, you should see as this group. Your group is the Z. The subgroup is NZ. Every subgroup in Z is normal. Okay, because it's abelian there. So you can just swap. Yeah. GA equals to AG in Z. 2 plus 3 equals to 3 plus 2. So everything commute. If commute, then surely normal. Everything is in the center. Every center is normal. I have to use that. Use recall. Please recall. Yeah. Every abelian subgroup is normal subgroup. And this abelian normal subgroup is normal subgroup. Yeah, I think so. Yeah, wait, let me think.
Yes,
okay, wait. This is a question. This is a proposition. I think this phrase is a little bit different. Phrased a little bit differently. Abelian subgroup, because abelian subgroup is center, so every center is normal. Okay, yeah. Wait. Let me think. Abelian subgroup maybe just abelian within the subgroup, right? Yeah, maybe you don't commute with the thing outside. Yeah, every center is normal. Yeah. Abelian subgroup and center is different. Center need to commute with everything. Abelian subgroup just say that within the subgroup they are abelian, they commute. I don't know whether it commute with outside element or not.
I commute with everything that I was saying. Then
if you commute with everything you have center, and then you are normal, correct? Right, abelian subgroup. A typical example of abelian subgroup is what? Cyclic group. Yeah. So you can go Sn. Sn is non-abelian group, and then you take cyclic group inside there. It's an abelian subgroup. Is it normal or not? This is an example you guys give in assignment 2, right? You dig out the non-normal subgroup and then intercept it and then show that it's not normal. Okay? And then normal also have two criteria, right? Whether it is normal within the big group or normal within the subgroup itself. Two types. So when you talk about normal, you need to say normal with which group compared to which group. Okay. That makes sense. I'm just recalling what is in assignment 2. Okay. Please recall your assignment 2. Okay. So so a prototype here, example here you should keep in mind is, for example, what is Z mod and Z. So in this case, we'll put Z bar at the top. And then okay, maybe we scroll down to 3Z. Okay. And then in 3Z here, how many equivalent class? So there are 0 bar, 1 bar, and 2 bar. Okay. And then this is just this, sorry. So this is 0, 3, -3, and then so on. And then the quotient of 1 is 1, -2, 4, so on. And then quotient of 2 is 5, and then -1, and then so on. Okay or not? Okay. So you can see here, 0 bar, 1 bar, 2 bar is a set. Last time I told you it's a set, right? What's this set here? This is the quotient. Okay, so these are the quotient. Okay, so these are the quotient. Any question with this notation here? Any question? Or anything unclear about this example? That not 3Z. Or we can write that. Is it clear about this example? Any question or not? Yeah. Okay, one thing I want to talk since Jimbo come already. Okay. For the assignment, right? This time, I think I'm quite happy about your assignment this time because you did spend time to find the solution. But because you find the solution, okay, but you don't understand what you wrote, so you just copy. So there's a lot of mistake, and then plagiarism. Okay, I sent out an email on plagiarism. If you haven't applied me, please do it soon. Okay. So if you cite answer from the internet or other sources, your friend, you should write it down. Okay, write down where you get it. And then when you read the solution, you should try and understand the solution. Okay, not just copy down the solution. Okay, so this is the next stage you have to develop. Search solution, understand the solution. Okay, write down in your own word. How to write down in your own word? One thing you can do is you change the notation. Okay, change the notation. Or you can produce your own example. Okay, for example, how I get the plagiarism of Jimbo solution. So Jimbo give a solution in GL2Z2. This is such a niche example, you know. I mean, it's very special. I give you a chance. How many possibility will you go to the GL2Z2? Okay, and I didn't promote this group. I didn't promote it. And how would you often go to that group? I promote it, but I didn't like over promote it. Say, wow, this is very good. You should know whatever, right? I just say once, there's this group. Right? So actually, Jimbo solution can be is working in GL and R as well. You don't need to go to GL to R. And this is what Thingy and Y did. Their solution is similar to Jimbo. Okay? The subgroup is, I think, the same. but the group is different. GRN is infinite, but still do the job. Okay. Yeah. So one thing to check whether you understand or not is whether you can change the notation or not, whether you can change slightly the solution or not. Okay, this is testing you whether understand what the idea behind. Okay. Okay or not? Yeah. And then so see, if you can search for solution, if you can understand and work it out, this is called research already. You're actually doing research. Okay, so because you are new, so do it step by step, step by step, step by step. Okay, search for solution, understand it, write in your own sentence. This is research. Okay, yeah. So please learn, please learn from mistake. And Jimbo tell me, this time he never ask people already. He don't go search internet. So how you study, Jimbo? Can you share with them? Just tell them how you how you study. Focus in class, and then what? What did you tell me? Focus in class and okay. One thing he did is he did tutorial. Every week he came to my office and asked. Okay, so please do it. Please do it. It's good for you. Okay, so training you to think. Okay, you don't need to ask people anymore. Independent thinking is what this course can give you if you don't want to do pure maths in future. Okay, independent thinking. Think, listen carefully. Independent thinking. 独立思考or 独立思维。Okay or not? Independent thinking. Okay, purely by logic. Purely by logic. Okay or not? If you want to get anything from this course, this is what you can get. If you want to, you don't play with group anymore. Or algebra. Does it make sense? Okay. Another feedback I get from Ming Xiu is sometimes the class go a bit too dry. What is dry? 干货. You know 干货, right? Chinese. 干货. What is 干货? Dry. Okay. So 很干. So maybe sometimes lack of motivation, lack of example, right? Because sometimes example is kind of long, so I don't want to spend time doing it. So you can ask me, you still can ask me, sir, too dry. Too dry. Okay. Then I'll try and give some, try and see if I can give, offer anything instant or not. Okay, you can ask me. If I cannot produce instantly, maybe I will produce next time. But you need to let me know your need. Okay, you can. Okay, you can do it in my class only. Okay. So you say, can you provide more examples or not? I don't get this abstract statement. Okay, you can ask like this. Okay. Okay or not? Okay, so yeah, you can ask me to give more example or motivate more. Okay. I will entertain you. But will depend on the speed or flow of the lecture. Okay or not? And then, yeah, because our lecture is, I guess, delayed by a little bit by 1 day, and then we took one lecture to get the exam, right? So hopefully we can be on track back. If not, maybe or not yet, we will do extra class, not sure. Or I take away some material, depends. Okay, so I just give you some preparation. Okay. Yeah.
And next assignment we delay a bit.
Oh, next week assignment, huh? Any reason you want to delay?
Because next Tuesday we have interview in. Next Thursday statistics.
Ah, okay. And
MA assignment also.
Okay. Maybe, okay. Can delay maybe,
Few days.
few days, enough. Monday, Tuesday, like that. Monday, Tuesday.
Yeah.
Monday or Tuesday, like that. Tuesday. Yeah. Yeah. Also, this delay will depend on my lecture speed also. Where I have to finish what the assignment does. So let's fix about Monday and Tuesday and then see how the lectures go and then we will.
So it's next to Monday.
Yeah. And then depend on the speed of the lecture and then we will decide the real date again. Okay? Yeah. Okay. Okay. Okay.
Okay.
But please don't start last minute. Don't start last minute. Okay? Please don't start last minute. Okay. Let's continue. So why we look at this coset here, set of coset here, okay? Actually, this coset form a group. Okay, they form a group. Okay, so this set form a group. So you should see these set as elements. Okay, they becomes elements. Okay, they form a group. So if they form a group, that means you need to tell me how two coset multiply. Okay, how two coset multiply together. Okay, how to produce another coset. Give me two coset G cross G, how to produce another coset in G. Okay, so we're gonna do this in a theorem style. Okay, so let's take a normal subgroup. Okay, and G bar denote the set of coset of n in G. Okay, then there exists a law of composition on G bar. Okay, making G bar a group. Okay, such that pi to G bar. Okay, so what's this map here? Remember what is G bar? G bar is just the set of coset. Okay, how you send an element to set of coset? You just send every element to its coset. Okay, you just send every element to its coset. Okay, so this map is a surjective map. So this is a surjective map. Not just a surjective map because we know that we make G bar into a group. So this is a map between group. So when you ask whether this is a homomorphism or not, actually we can extend it as a homomorphism. And then what's the kernel here? Anyone want to guess what's the kernel here? What's the kernel here? Okay, maybe you cannot just guess. So the kernel is n. Okay, this is the why the rationality of putting G mod n here. Okay, we send n to, so we mod up by n. Okay. So why is it a 0 in Z mod n? Okay, we will soon see later why n is 0 in the set of coset here. Okay, there's some terminology here. So remark, the mag I is often referred as the canonical map from G to G1, G bar. Okay, so we'll call this map a canonical map. So meaning this is the normal, the direct map, the obvious map that you will think about it. That's why we call canonical. Whenever you heard about canonical, is it means normal, direct, obvious. Okay, obvious map. You will define it. Okay. So there are few things to do to show this theorem here. Okay. You can forget about the statement now, but listen what you need to do. And these four things will tell you again what's the statement you need. Okay, there are four things to do here. Okay, first, we want to know how to compose, okay, inside my G bar, okay, or the set of coset, how I combine two coset together, okay, LOC. And then prove that this LOC really give me a group. So to give a group, what you need to check? Huh? What do you need to check to make something into a group? So associative, as, associative, identity exists, and then inverse exists. Okay, you need to find these things inside this set of concept here. Right. So we go back to the first lecture again. We have a set. We want to combine things within the set. Okay, combine elements within the set. And then third, okay, we need to settle that, prove that pi is a surjective homomorphism. Okay. I define pi, right? Pi, what's the pi map? I send every element to its coset. Okay, I send every element to its coset. So this example can see from here. Okay. I take all the element in Z. Okay. For example, 10. Okay. Under pi, where should 10 go? Here. Which coset should 10 go? So example, pi should send 10 to where? Which coset? Coset of 1. Correct? Yeah. Okay, because 10 live in the coset of 1. Okay. 10 live in the coset of 1. So 7, 10 here. So I live in coset of 1. Okay. So this is what the pi map doing. 10 will get sent to 1. Okay, 4. Prove that actually the kernel of pi is actually n. Okay. So this is the 4 things we need to do to recover the statement here. Okay, so what's the obvious LOC you can do on coset? If I give you AN, I give you BN, how to combine them? How to combine them? What's the obvious thing you can do? Union. Union of subgroup is not subgroup, okay, but this is coset. So maybe union of coset, maybe not coset. You try and prove it. I mean, give some example. So what can you do? Yeah, okay. Yeah. This is coset. I think so, yeah. No, I mean, coset, is it a coset of some normal, some subgroup or not? This is the question. I think it's not. You can try and check whether union of coset is a coset or not. Side question here, you can check whether union of coset is a coset. Is again a coset. Okay. Okay, just keep this side question first. Okay, so what's the obvious thing you can do? You just multiply them. Okay, so why does this work? Okay, because you can associate the set. Okay, note that these are these are equality on set. Okay, these are equality on set. Okay, but on the level of element, you can associate. Okay, on the level of element, you can associate. For example, let's say I want to take A N1, B N1, N2. Okay, is it true that it is equals to A N1, B N2? True, right? It's just associativity. Okay, so that's why I'm abusing notation here. I do associative on set. Okay, so you need to take note. This is set, but B is element and A is element. Okay, so what am I doing is I'm showing equality on set. So you need to check on the element level. Okay, so and then what can we do? Just now Wayne said that if my set is normal, then the right coset is equal to the left coset. Not just equal. I can use the same x to build the left coset. So meaning what? Meaning I can commute the element with the normal. So I can make it into Bn. Okay, then I associate again, it's just A, B, and N. But N is what? Is a subgroup. Okay, N is a subgroup. So I can just write A, B, N. What is A, B, N? Another coset. Okay, so I send the product of two coset into coset. Okay, so how I multiply two coset together? I'm just multiply on the level of element. On the level of element. Why is it equal here? Because I go from left to right, go from right to left. I'm just using associativity. Okay, on the level of element. And then here, how I combine? I also combine on the level of element. Okay, N1 times N2 is always in the subgroup. Okay, it's because it's close. Okay, so this is how we multiply coset together. Is this a group or not? Okay, I think associative is obvious, right? Because it's associativity on the level of element. Okay. How about identity? Who is the identity? Who is the coset that I always multiply, get back the same coset? An times what coset always get back an? N. Okay, so N is the identity in my group here. Okay, not yet group yet. Just set of coset. With law of composition. Okay, associative law of composition. And then who is the inverse? So I give you An. Who is the inverse? It's just A inverse N. Right, you can see from this calculation here. If I replace B with A inverse, okay? If I replace B with A inverse, what do I get in the end? I get A composed with A inverse, which is identity times N. So identity times M is what? It's just N. Okay, I get back the identity. Okay. Okay or not? So you see, there's order here actually. I'm not randomly picking order. So you cannot decide inverse first if you don't know the identity yet. Okay, so you need to know about the identity first, and then you decide for inverse, because the definition of inverse relies on identity. You need to compose to identity. Okay, 所以这里的顺序很重要啊，我不是随便选 identity 先 inverse 后啊，因为 identity 因为 inverse 的 definition 是 define on identity， 我要 compose 后我拿到 identity， 所以我要决定属于是 identity。OK。Okay, this one done. Okay, so this is a group. So we show that we make G bar into a group. This group is very convenient. Come in handy. What's the next thing? So next thing we want to prove that pi is surjective. Okay, this thing is surjective. A go to A n. Is this surjective or not? If I give you any A n, can you find me an x or not?
Yes,
How? If I give you yn, take y. If I give you wn, you take w. That's all. Okay. So it's subjective. Okay. So it is obviously subjective. And maybe you will ask a point, then what's the point of doing this? So obvious. Okay. The point is like this. The point is like this. Go back to my example just now. Okay. I have 1 bar. Okay. I also have 3 bar. Oh, sorry. Don't want 3 bar. 4 bar. Okay. So if follow our argument here, 1 bar, what is the pre-image? So 1 bar is equal to 1 plus 0 bar. Okay. And then 4 bar is equal, sorry, correct. So 4 bars is equal to 4 plus 0 bar. Okay. So what is the pre-image of 1 bar in our example just now? So our example is from Z to Z mod 3Z. Okay. So who is the pre-image of 1 bar? To test whether you really know what I'm saying just now. So I said that just now we said that pre-image of 1 AN is just A. Okay, so pre-image of 1 bar is what? 1. Pre-image of 4 bar is what? 4. Good. Okay, you can see that. What's the significance about this? We actually know that 1 bar is equal to 4 bar. These are the same whole set. Okay, but they have this different pre-image. Okay, does this break any rule or not? Does this break any rule? Same image, different pre-image. Does it break any rules or not? No, right? Because you can have many to one function. Okay, so this doesn't break any rule. The things that break rule is 1 to many. Okay, this is to check whether the function is well defined or not. Okay, but doesn't break rule. You can have many pre-image that get sent to the same image. This means what? This function is not injective. That's all. That's why we can only deduce surjective here. Okay, no injectivity. Okay or not? So you need to appreciate what is injective, what is surjective. Okay, when is the function well defined? 3 things. When you talk about function, you can straight away check these 3 things. Okay. Next. Okay, last thing we want to do is to prove that the kernel of pi is n. Okay, is the kernel of this pi n or not? How to check this? So what's the identity in G bar? What's the thing that gets sent to? What's the thing the kernel of pi is sent to? I'm asking already. Where's the thing that kernel of pi gets sent to? Correct. So what's the identity in G bar? N. Okay, the identity in G bar. So our map is sending A to AN. Okay, so you want to make sure that check A
such that an equals to n. So what a does this identity, or any a inside my normal subgroup. Okay. So check a such that an equals to n. Okay, this shows that a must be in n. Okay, all the a in n works. Okay, so this means that this implies I equals to n. Okay, so actually we have this direction here. So actually we only get this direction. The other direction is obvious, I would say, because pi send n to n. Okay, and then we want to find what is the thing inside this kernel. Okay, so let me write down the full argument for you. Okay, so full argument. Okay, suppose S is in kernel of pi. Okay, we want to show that X is in n. Okay, so since X is in the kernel of pi, by assumption, pi x is equal to n. Okay, which means xn equals to n. Okay, and then this implies that what are the elements that multiply n give you n? These are all the elements in n. Okay, so this is what we want to get. Okay, you can multiply e here, en times everything in n, still in n. You can also multiply other element in n, because n is a what? Subgroup. Okay, so you can multiply everything inside here. So this prove one equality, no, one inclusion. This prove that kernel pi is in n. Okay. How about the other direction? To show n is in the kernel of pi, okay, we just need to show this is true. We just need to verify that pi of n is equal to n. And this is obviously okay. Not I put obviously true here. Don't abuse in your assignment. And obviously true doesn't mean you don't need to do anything. I just say that the thing you need to do is very direct. Okay, when I say obviously true, it just means that the thing you need to check is direct. Why I'm saying it's direct? Because you just need to read on this line. What is pi n equals to n means? N is an identity. Everything that sends to identity is in the kernel. Okay, it's just definition. So surely n have to be in the kernel of pi, because this is the thing that gets sent to the identity. Okay. Oh, vacuously is another story. Vacuously is not obviously. Vacuous, vacuous, what is vacuous? Vacuum. Nothing. So vacuously true is there's nothing to check in. When is the case you use vacuously true, do you know? It's false. There's one example I can give you on the spot. So for example, Y empty set is a subset of Y empty set is a subset of, for example, a set of containing our empty set. Okay, why is this true? Okay, you need to show that. Let me think. Okay, so what you need to show? You need to show that everything here is in here. Correct or not? Everything for x in phi, then x is in the right hand side. Want to show. But is there anything in phi or not? No, there's nothing. I think there's nothing to check. Recursive true. Or like what you said, the thing you need to assume is false. So there's if false, then you imply everything. False can imply everything, you know. False implies false is true. False implies true is true. So that's why we are particular of being whether it's true or false. If it is false, you can deduce everything you want. You can deduce nonsense. Okay? False can deduce nonsense. Okay? 错的东西为什么？词汇不够 ，imply 这种。OK， 可以推导出一切。OK， 错的东西可以推导出一切。OK， 所以我们对错的东西不在意，因为它错的对的都可以推出来。所以我们在意的东西是对的，这个东西对吗 ？OK， 不对我们不在意，因为
So he says it's not handsome and everything is true.
Okay. 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 So, yeah. When closely true is different from obviously true. Okay. Let me. Okay. Let me do one remark, and then we will take a break. Okay. So one last remark. So in G mod n, right, we really have to make sure our n is normal. Okay, because remember that only in normal we have the left and right coset can commute. Commute, not the real commute. So otherwise, for example, we can easily look at one example here. So consider an example which is, let me see. So what is the example here? Symmetric group. So what's this example here? I think it is 1, 2. Let's look at this group here. This group is not normal, right? In symmetric group, because this is not an even commutation. Okay, so we can look at the product of two cosets here. For example, I take H, and then I take 1, 2, 3 H. Okay, what's the set of element we get here? So we need to recall what is inside H. So H is obviously E and E2, 1, 2. And then what is here? So I have 1, 2, 3. 1, 2, 3 times 1, 2. What do you get? I think you get 1, 3. Okay, and then what's this coset here? So if I multiply here, what do I get? I get 1, 2, 3, 1, 3. And then 1, 2 times 1, 2, 3, I get 2, 3. And then 1, 2 times 1, 3, I get 1, 3, 2. Okay, so is this a coset? Is this a coset? If I multiply two cosets together, do I still get a coset? Is this a coset? Question. Is this a coset? Coset partition the group, right? So my group got how many elements? 6. So these are the two different cosets already. 1, 2, 3, 4, 5, 6, 7, 8. More than 6. And also last time we learned that coset always have the same order of element. Right. Every coset is the same size. So this coset here have 2 sides. So all the cosets have 2 sides. But here we got 4 different elements. If it is a coset, at least the number should go down to 2. Okay, so you see, if it's not normal, then multiplication of coset doesn't necessarily give you a set. Okay, so we have to start with a normal subgroup. Okay, consider all the coset and then they form a group. And this is a very nice group. We call it a quotient group. Okay, we divide group by normal subgroup. Okay, we only can divide group by normal subgroup. Okay, let's take a break until 9:07. In the meantime, I will take attendance. Now we are halfway already. Take the news and new attendance. Yeah. Okay. Venus not here. 乐天、武泽、okay. 三儿、严科。严科 are you meeting me later or not? Are you meeting me later? 德瑞、Raylan、思雨。Where is 思雨啊？ Anyone know? Where is 思雨？ Not here. Seng. Seng, do you know where is 思雨? Okay. 孙林go toilet. 海仁 ，OK。金波，华英 ，Tishon， not here。英奇 ，OK。何怡，雪岩 ，Yes。嘉业，李凯，袁家，文硕，一定。玉维 ，online。燕博 ，OK。本业 ，Yes。林金 ，OK。董洁 ，Oh，Yes。英语，柳晴 ，OK。真诚，说宁 ，Where is 说宁啊 ？Anyone know about 说宁？说宁 ？Exam 啊 ，today exam is it? You guys have exam today? You guys have exam today? What exam? Academics. D. 天。何轩。何轩排到这。莹莹。Grace。张烨。嘉文。OK。明秀。Michelle。Michelle。哇 ，Michelle。哇，有按球。Ryan。OK。Ellie。雪梅。袁 also not here. So Ying and Sang later meeting me, is it?
可以抄
抄吗？
我们前面抄到
你要抄吗？你要抄吗？
你的 slide 呀，
等一下啦。
不要
啊？
哦，对哦，
我找东西先。
我等下可以一边吃瓜一边抄。
那 YouTube 啊？
那个口塞的，刚才那个油烟，你讲的是那个 argue，
Yeah。啊，口塞的 argue 什么 argument？
就是那个口塞有的
啊？
是不是一个口塞的 group？
不是，
那再问一次，你不是一个问题啊？再问一次。
没有，因为我刚才是那个我只看得到那个 partition 的
partition。
你们是讲口塞的时候，我想要 partition。
可以啊，然后
是讲那个
口塞存在一起。
union
union 对 union
是不是？
你口塞是说我口塞我可以去切，我可以拿口塞去切，可以 partition。但是我现在是抽一个 partition 出来 ，partition union partition 是不是还是 part of 一个 partition？ 这个是他的问题。明白吗？
整个大个的
something 哦，它是不是 ？OK， 这样子你这样子讲，什么叫做 coset 是 partition？ 就是说 coset 分成 partition。我现在 union of coset 就是说我把拿两个 partition union 起来，它是不是另外一个 coset？ 就是说它是不是另外一个 subgroup 的 coset？ 明白吗？
那个是因为它两个，这是一个吧？
没有那个。没有，它两个 union 起来变成一个 set 了嘛，对不对？那它是不是一个 coset of 另外一个 sub？ 不一定要那个 subgroup， 可能是其他的 subgroup， 肯定不是那个 subgroup 嘛，因为那个 subgroup 已经切到分到很好了嘛。但是问题是它是不是别的 subgroup？不是 always true， 我只能说， 你可以想象什么时候它出？它要出的时候，一定要是 follow 那个 Lagrange theorem 的吗 ？At least 你都要 follow 那个先。Then 你再 decide 谁是它的 subgroup， 有没有可能？反正它 generally 应该是错的，我觉得。confirm 错了。
因为老师给他爆炸。
OK 了 ，one way to show 是你 union 过后那个号码不能够 divide 那个 group 就 OK 了，因为每一个 subgroup 就要 divide 嘛，然后你不能 divide 你就不能了。但是假设它能够 divide 的话，你能不能永远说它是一个 concept 呢？那是下一个问题了。要不要做？要不要做？
他的西瓜炸坏。
哦啊 ，OK， 没有，等下再讨论我们要打。OK， Okay, good. Let's keep continue. I think we have a good momentum here. Let's continue. Okay. So next, this is a very, very important takeaway message from group theory. This is called the first isomorphism theorem. Okay, this is a very important theorem you need to take away from this course, okay? If you ever learn group theory, you should say that I learned first isomorphism theorem before. Okay, so what is this? So let's take a surjective map, okay? Surjective homomorphism. With kernel n. Okay, so it's surjective, right? Surjective, we can get a kernel, get the kernel out. And we can consider the quotient group. Okay, so kernel is always normal. Okay, so we can divide my group using n. Okay, so I give you a high class a bit language. We don't say divide group, we will say mod g mod n. Okay, g mod n. Okay, because we are not doing division in number anymore. Okay, we will say g mod n. So why use mod? It's exactly the integer modulo n. Okay, we are trying to imitate integer modulo n, mod n. Okay, so we will call the quotient group G bar, which is G mod the normal subgroup. And this is isomorphic to the image of phi, okay, which is G. Okay. Let pi G to G bar be the canonical map. Okay, recall the canonical map we defined just now. Okay, what's the canonical map we defined just now? We send every element to its coset. Okay, A to AN. Recall, this is just definition. Definition. And then the claim is, where's the isomorphism? Where do I find the isomorphism? Okay, so the claim is there is a unique isomorphism. Okay, there is a unique exclamation mark isomorphism. Call it a phi bar. Okay, from G bar to G prime. Okay, such that phi is phi bar composed with prime pi. Okay, so this is by assumption surjective homomorphism. This is the canonical map, and then this is what we newly defined, and then they equal. Okay, so how to picture this? How to picture this composition? This composition is very easy to picture once you get the diagram right. Okay, so the diagram you need to draw is, I have a G. Okay, I have a map. Okay, from G. So wait, how about I just make these guys smaller? Let me make some space for me. Okay, I just make a surjective map. Okay, from G to G prime prime. Okay, so this is phi. Okay, how about pi? Pi go from where to where? Pi go from G to G bar. Okay, so there's two paths out of G. Okay, and then the claim is I have a path back from G bar to G prime. Okay, I have a path going back here. And then this is what I define as phi bar. And then these two paths agree. Okay, these two paths agree. G, sorry, I put too many primes, so here remove it. Remove it. Okay, yeah. Okay, yeah, it's the same. It's the same codomain. Okay. Yeah. Can see or not? Can see? Can you see? Okay, so we will say that this diagram commute. Okay, if it is agree. Okay, if it agree. Okay, so I can go to G prime. Okay, through phi. Okay, I can go to G prime through through pi and phi bar. Okay. Okay. Any question on this diagram here? Or the equation? Any question? Any question? Any question? So there are two paths go to G prime. Okay, they should agree. That's all. Okay. Yeah. Canonical. 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 What is that? Just now I said, right, what's canonical map? So canonical map means obvious map. Okay, why is it obvious? How to define this obvious map here? G to G bar. Okay, the obvious map is to just send every element to its coset. Okay, this is what we call the canonical map. Okay, yeah, yeah. Here I wrote it here. Pi is the canonical map that sends the element to its coset. Any other question to understand this segment here? Yeah.
So the group homomorphism.
Yeah. You first. Yeah, right?
So the group homomorphism can be any group homomorphism.
No, not just any, right? Need to be surjective. Surjective. You have a kernel. And then other question. Linear functional to matrix. What's that? You mean what kind of transformation? Then can I give an example? Yeah, sure. So I want to give the same example, Z mod and Z. Okay. I can give an example of Z mod and Z. Right. Okay. So what do I do here? So I want, so example, let's take an example. Let me think. So let's take our G as Z. Okay. And then G bar is Z mod and Z. So what's my G prime here? What should my G prime be? Or what is my phi has to be? Let's think about this. What is my phi here? Okay, maybe I don't put NZ, I put 3Z. Okay, I put 3Z. Okay, let's determine what is the phi here. So what's the morphism that has 3 as a kernel? Multiple of 3 as a kernel. What's the map that give you kernel with 3? So what's the map that sends 3 to 0? What is the map that sends 0 to 0? What's the map that sends 6 to 0? Minus 3 to 0, minus 6 to 0, 9 to 0, 12 to 0, 15 to 0. What is that map? Mod 3. Yeah, mod 3. So you just take mod 3. Okay. So you send, what do I mean by mod 3 here? You send every element x, go to x mod 3. That's all. Okay, what is mod 3 means? Tell me the remainder after you divide by 3. Okay. If you divide by 3, your remainder is 0, then you give me 0. Okay, if 1, you give me 1. If 2, you give me 3. Okay, your remainder won't be greater than 3. And so this is the surjective map. Okay, what's in the kernel? All the multiple of 3. Because 3 mod 3 is 0, 6 mod 3 is 0, 9 mod 3 is 0, 12 mod 3 is 0, 0 mod 0, 3 is 0. Okay, all the multiple of 3 is 0. Okay, so this is an example of this. And any other question you want to ask before we prove it? Okay, what's phi bar for this? What's phi bar of this? So, what is phi bar of this? Okay, good. So what is phi bar of this? So phi bar have to do what? Phi bar have to send element in okay, I do something stupid or not? No. Okay. So I have to do G prime to G prime. Sorry, G bar to G prime. Okay, so meaning this phi, okay, phi is here, phi bar, have to give me a coset. You need to tell me where it goes to Z. Okay. So how do I define this? Okay, let me go into a little bit into this proof here. So we will send the coset to just phi of x. Just evaluate this coset by phi. Phi we know, right? Phi is given. Phi of x, what does it mean? What does it mean? This means that I look at the representative. I look at the representative. Okay. Phi apply on the representative. So for example, so 1 bar will go to phi of 1. Okay, the representative of 1 bar is 1. So what is phi1 here? Phi1 here will be 1. Good, because 1 mod 3 is 1. Example, again, just now, same example. Let's say we take 4 bar, we change representative. Again, we change representative. This will go to phi 4. But phi 4 is what? It's also 1. What am I doing here? These two are the same coset or different coset? Same coset have to send to the same place so that this function is well defined. You see, they are seemingly different. You see, here we are evaluating different things, but they give me the same image. But here they are the same. Okay, so this is to check that this phi bar is well defined. Same things get sent to the same place. Have to be 1 to many or 1. Sorry, 1 to 1. Yeah, 1 to 1. 1 to 1. Yeah, 1 have to 2. Yeah. Not exactly. I just mean one element have to send to one image of it. Okay. Okay, or not? You see, even though we evaluate at different two numbers here, two different representatives, they give me the same number. Okay, or not? Yeah, so that's why very important to check well-definedness, okay, in this class, because you almost every time start with a different, seemingly different things, okay, but they give you the same. But as a concept, they are the same. 1 bar and 4 bar is the same. Okay, but you know that 1 and 4 is different. But after phi, come the same. Okay, so this is a nice place about algebra. Same or different, different or same. Okay or not? Okay. Yeah, so this is a typical example for this theorem here. Okay, and so let's go into this proof here. So I already told you how to define this isomorphism here. Then what do you need to check? You need to check that this map is a homomorphism. Okay, it's a homomorphism. Okay, so meaning what? Meaning you want to check. So first check homomorphism. So few things you want to check. Check that phi bar is homomorphism. Okay, the homomorphism. So homomorphism, what do you need to check? That is, if I take two cosets together, okay, do I split out the coset? Okay. And then second, I want to check injective and surjective. Okay, injective and surjective. Injectivity, surjectivity. Okay, let's have a check on the homomorphism first. So how to check homomorphism? So phi of x bar y bar equals to what? X y bar. S bar y bar is equals to phi of x y bar. Okay, just now we computed. AN BN is equal to ABN. Right, this is the group property, in quotient group. And then this is by definition what? Phi of x1. Okay, but phi is a homomorphism. I can split. And then I can use definition of phi bar again, which is just phi bar x bar and phi bar y bar. Okay, yeah, so it's a homomorphism. So whether or not is it surjective or injective? Okay, is it surjective? And so surjective on where? Surjective on G prime. Okay, is it surjective or not? How? Why is it surjective? Phi bar x bar is defined to be phi x. Okay, so the question is if f bar if phi bar surjective or not. So meaning for every y in G prime, okay, we want to find pre-image of y, okay, call it y bar, y bar, such that phi bar of y bar equals to 1. Okay, can you find y bar or not? Okay, but this implies what? This implies phi x equals to 1. Okay, but phi is surjective. Okay, so phi will give you an x. Okay, since phi is surjective, there exists an x such that phi x equals to y. Okay. So here is y bar, sorry. So phi x equals to y. Then who should you take for y bar? Yeah. A bit weird, is it? A bit confusing. So let's change the pre-image to z bar, okay? There's a z bar. Okay, and then we want to find phi z equals to y. So since phi is surjective, there exists an x such that phi x equals to y. Okay, then we just take z bar equals to x bar. Okay, because phi bar of z bar equals to phi bar of x bar equals to phi of x equals to y. Okay, does it make sense or not? So the surjectivity coming from phi, because this is how we define phi bar. Okay, this is how we define phi bar. Okay, okay, because this is how we define phi bar. Okay, so the surjectivity coming from here. Okay, the phi will give you the right concept to start with. Okay, okay. Any question? Any question? Please ask. Please don't be afraid. So this proves that this is surjective. How about injectivity? Suppose phi bar of x bar equals to phi bar of y bar. What do we want to show? We want to show that the two cosets actually equal. Okay, we want to show that two cosets actually equal. But phi bar of x equals to phi bar of y implies what? We get phi x equals to phi y by definition. Okay, so this is by assumption and definition. Okay. By definition of phi. Okay. And then what does this give? This tells us that phi of S y inverse is the identity. Remember, we can do the homomorphism stuff. So step by step, we have multiply the y inverse on both sides. Okay? And then we use homomorphism. But this one tells us what? This tells us that xy inverse is in the kernel of phi. Okay, but what's the kernel of phi? Kernel of phi is the n. Okay, so this means what? By the TFAE statement, if you know that xy inverse is in n, this implies that by proposition before, it tells me that the two concept is the same. Okay. Very good, very useful proposition. The thing we showed last time. Let me just quickly point to you. Anyone know which lecture is it? Yeah. So when we define the concept, okay, this one. Okay. If I have xy inverse in the kernel, then the two left concepts are the same. Okay. If you want to deduce why is it true, it is this proof here. Okay. As long as you get this line, then you will get this line. And these all are equivalent. Okay. Yeah. Okay. Any question so far? Any questions so far? And there's one last thing we need to prove, right? Okay, we know that it's isomorphism. Actually, we need to show that it commutes. Okay, it commutes. Okay, why is it commutes? So on the top, we send x to Vx. Okay. At the bottom, what do? We first sense x to xn. Okay. And then this is what pi did. Okay, this is what pi did. Pi send x. The canonical map. Get the canonical map. And then next we use phi bar. Okay, what does phi bar do? Phi bar sends xn to x. Right. So we send n to Vx. Sorry. Okay. So let me write down. What is phi? So what is phi bar xn? Phi bar xn is defined to be equal to Vx. Okay. So the top you got Vx, bottom you also get Vx. So they are equal. Okay. Okay. And then in this case here, we will say that phi factors through phi bar. Okay. Phi factors through. Okay, any question about this theorem here? So one typical example you need to keep in mind, you can keep in mind is this one. Okay, the Z mod 3Z. Any question? So in this case here, so the notation here, so the notation, the terminology, okay, terminology here, we will say that phi factors through G bar. Okay, factors through G bar. Because you split your phi into composition of homomorphism. Okay, so phi factors through G bar. Okay, because you split your phi into two parts. Okay, factors through. Okay. So maybe let's look at more example of G prime. Okay. So before that, we will make a corollary here. So this is what the statement I made just now. So corollary, let phi G to G prime be a group of homomorphism with kernel n and image E prime. Okay, the quotient group G bar. Okay, or we write G mod n is isomorphic to X prime. Okay, so this reflects what we said just now. Every normal subgroup is a kernel of some homomorphism. What is that homomorphism? That homomorphism is exactly the canonical map. Okay, that canonical map. Okay, you have a normal subgroup, and then you can consider G mod n. Okay, and then this n is a kernel of what morphism is the canonical map. Okay, it's a canonical map. Yeah. Okay, so that canonical map is quite useful here. Let's look at few examples, right? Let's look at a few examples. So just now we already know that Z. So if I consider Z to Z, okay, and then we take out the mod 3 kernel, then we will get what? So the kernel here is 3Z, okay. Then we will get Z mod 3Z, which is the same as Z3. Okay, so that's why in the early course, right, when we write Z mod 3, we'll write this, we'll either write this or either write this. They are the same. Okay. But why sometimes I don't write equal here? Why I don't write equal? Why are they not the same? Okay. Oh, I think it's correct. I think it's correct. So what does it mean by what did Wayne say? So element wise, these are not the same. So Z3 I can just consider as C3 for example. So for example, here is just 0, 1. So here is just a cyclic subgroup generated by 3. Okay, for example. So in this case here is 0, 1, 2. Okay, but on the left hand side here, this is equivalent class. Okay, so these are set of set. Okay, so they're not equal on the north. But often we blur the distinction between these two because they are really isomorphic. So we blur the distinction. So maybe sometimes we abuse notation. Z3 is Z mod 3Z. Okay, and Z mod 3Z is Z3, is a cyclic group. So we blur the distinction between these things. Okay, because they are isomorphic as a group. Okay. Yeah. Okay or not? Yeah. They're just isomorphic. They're just isomorphic. If they are isomorphic, they have the same property. They have the same multiplication. Because it's injective. If it is isomorphic, that means there's an injective and bijective map. Not only that, this map respects the multiplication. Right? Homomorphism. Vxy equal to Vx times Vy. So what does it mean by respect the homomorphism? Remember the commutative diagram I drew last time? You can multiply first and then you send over, or you send over first and then you multiply. Okay, another few example here. So for example, this map here last time. There are few maps we talked about with a kernel, right? We can consider all these. So just now actually I picked it up already. So it's in lecture 7, I think. Yeah. Okay. So you can ask the question, what is GLN mod SLN? Okay. What is SN mod AN? Okay. This mod the 0 subgroup. And then this mod KN. Okay. And then CX mod U. And then R mod Z. Okay. You can ask about this. What are these things? Okay. What are these groups? Okay. So let's take few examples here. So for example, we can consider this map here. This map is the absolute value map. Okay, you compute the length of complex number. So what are the complex number that get sent to the identity in the multiplication of real numbers? Okay, these are precisely the root of unity. Root of unity have length 1. Okay, so you can ask about what is CX mod the kernel of this map. Okay, so what is this? This is actually just the Rx. Okay, you can think how to think of this. How to think about this? How to think about this? So let me draw some picture. So you can think about CX as a group, Rx, XX, another group. Okay, and then you should see that every element in Rx, right? Okay, there's some A plus Bi get sent to this number here. For example, 2, which length gets sent to, so let's say this is A1 plus B1, A2, B2. How does who get sent to P2? Who has the length of 2? Okay, this is actually very easy to achieve. What do I mean by that? So let's say I got an R here. Okay, I got an R here. Whose length has radius R? You need to know about the De Moivre. No, okay, that one is De Moivre formula. So that's a polar description of complex number, right? You can write A plus Bi as radius times e to the I theta. Okay, you just pick this guy. Then this guy will have the length r. If you take modulus of this, right? Okay, it's the modulus of r times modulus of e to the I theta. But e to the I theta, you will always get between -1 and 1. Okay or not? Okay? Yeah, so it's surjective. So if I mod up this e to the I theta, what happens? Okay, I'll get all the r again. And then what else? Second, if I take GLN, mod out SLN, okay, what do I get? I also get R cross. So what morphism I'm considering here? So what's the morphism I'm considering here? So I have a map from GLN to R cross, which is surjective. What is this map here? This is the determinant map. Okay, so this is the determinant map here. Okay, what's in the kernel of this determinant? It is exactly the SL and R. Okay. So how to produce this isomorphism? This isomorphism is exactly produced by the surjective map. Surjective map, right? You just leave out with injectivity. So how to produce the injectivity? Cut out the things that don't give you the injectivity. Throw them away. I don't mean throw them away, but they get combined. They get combined. They don't throw away, they combine. Okay? So, okay, one picture I want to show you. Another watermelon picture here. Okay. If anything you don't remember from group, I'm sure you know how to cut a watermelon. So, we have a group here, and then G prime here. Okay? Previously, what did we say? Okay, now we want to find a normal subgroup here. Okay, normal subgroup. Because we have a subgroup, right? We can partition my group. Okay, we can partition my group. So I got N, we got AN, BN, CN. Okay, like this. Okay, let's say we have a phi. Okay, phi with kernel of phi is exactly N. Very good. So what does it mean? This means that if I send everything in N here, this guy will get sent to the single element, which is the identity. Okay. And then what does this tell you about all the other elements here? All the other elements here will get sent to phi A, phi B, and phi C. Okay. Okay, so this is a generic group homomorphism. Again, let's draw some more generic group homomorphism. Look like this. Okay, so this gets sent to this. This gets sent to this. This gets sent to this. And then this one gets sent to. Okay. So maybe a priori there are more things inside here. Okay, but let's say that our morphism is surjective. Okay, surjective, meaning what? Phi of G equals to G prime. Okay, so these are all of them. 4 quotient correspond to 4 elements here. So is this map injective or not? Not sure. Why is it injective? N is a set. There are more than 2 things get sent to the same thing.
Oh, you mean the set?
Yeah.
Oh.
If N is trivial, if N is trivial, then it is injective. But if N is non-trivial, it is not injective because more things can get sent to same thing. Okay, so what to do? We mod it up. So we consider this N. So we squeeze. So what do you think is we contract this portion here. So we contract until we have just 4 points here. N, AN, CN, and BN. Okay, we contract to a point. All these set we just consider as one thing. Okay, this is what Gmod NZ is doing. Gmod N, sorry, Gmod N. Okay, so this is the picture of Gmod N. Okay or not? So this is the picture of Gmod N. Let me finish first. So and then N will get sent to E. Okay, Cn will get sent to VC. Dn gets sent to VB, and then AN gets sent to VN. This is what? This is the phi bar map we defined just now. Okay, and then how to go from the top picture to the down picture? This is the canonical. This is the Jimbo asking one canonical pi map. Okay, so what pi do? Pi this subgroup into 1 point. Okay, so then you will have point correspond to point. So this is an injective map. Okay, so this is the picture you have to put in mind when you do this question here. Okay. This is the picture you need to keep in mind. So what am I doing if I mod out by n? I contract the set into 1 point. Okay, we consider the set as one element. Okay, so that we have injective in this case because it's point to point. It's not set to point. Okay. Okay or not? So this is the idea you have to accept first and then try and read the definition again. Again from my lecture, not from the textbook. You need to keep this picture in mind. Okay, what does the canonical map do? The canonical map squeeze everything together. Okay, so that's why this thing have to have something to do with topology because there's some contraction here. Okay, and then any question or not about this picture here? How to understand this picture? So this is the triangle. Triangle I drew just now. First isomorphism theorem. What time is it? 1 minute. Okay, we have to finish within 1 minute. Okay, I don't want to spend more time first. So let's finish two statements and then we will call the day. So there are also, because we have first, right? There are also second, there are also third isomorphism theorem, but we won't prove it in this course. If you are interested, you can have a look. We won't emphasize much about this, but it's kind of interesting. For example, second isomorphism theorem says that if you have a subgroup in G and then a normal subgroup in G, what do? H times N, the product group, over N is isomorphic to H over H intercept N. Okay, kind of interesting. You can try and prove it. And let H K be a normal subgroup of G. Okay, and then K as a subgroup of H. Okay, what do we have? We can take G mod H, but this is equal to G mod K over H mod K. You can see that somehow the fraction property comes out in this group mapping property. Okay, so it's really a generalization of a number. Okay, can see a number. If you somehow can divide this, it's like G times K times K over H, which is G over H. But this is not what it means, but kind of generalization of the number. Okay. And one upshot, how to produce this isomorphism. Okay, G mod N with its image. This is just coming from the surjective map. You need to find a surjective map first, and then show that what you're modeling out is the kernel of that map, and then you will show that this is injective. This is isomorphism, which is exactly what this picture tells you. I squeeze all the things inside kernel into 1 point. Okay. Have more questions? bring it next lecture. It's fine. Okay. You don't understand now, it's totally fine. But if you don't ask next lecture, then it's not fine. Okay, please bring it next lecture. Okay, yeah. Read it first. You got question, bring it next lecture. Okay, we should see you next time. Yeah.
那 contraction 是 板 up 的。
啊？
那 contraction 那东西是板 up 那边。
什么叫板啊？
我刚才看，我之前看到我 contract 板 up contraction 的。
啊？
我之前把一个
这个比较简单了。
跟他你翻成一个